Okay, we'll continue with chapter 10, and here is a little bit more detail on the principle of fossil succession. So remember, it's a systematic appearance and disappearance of species through time. And William Smith identified fossil assemblages, these fossil assemblages found in limited intervals of geologic strata. And so figure 10.3 in your text shows some of this, and there's an error in the text here. A fossil F should be younger than fossil A when you read about that. But let's look at the figure. And so on this figure, on page 310 of your text, or in chapter 10, note that there are trilobites, graptolites, brachiopods, ammonoids, some other gastropods there, some bivalves. And so you can see that each individual species has its own fossil range. For example, these bivalves first appeared in the fossil record at this point and continue on to the present. And then, for example, the graptolites appeared here at this level and have disappeared there. So these represent the fossil ranges. So we use assemblages. For example, if we're looking at the strata number 5, for example, and we saw both brachiopods and ammonoids, well, we can restrict the limit of that because even though brachiopods have a much larger range, the ammonoids have a narrower one. And so we see that with the age of this formation would fall in this region here, even though we have all those brachiopods. Now, let's look at an example that I have, is looking at plankton, fossil plankton. And these fossil plankton are called foraminifera. So remember, the foraminifera are the amoebas with shells. And so these are the different foraminifera. They have various names. And note that these bars here represent the age ranges. For example, Globotruncana Maya first appeared in the fossil record at about a little over 80 million years ago, and went extinct at about maybe 74 million years, or 64 million, 65 million years ago up here. And so whereas this foraminifera, Globotruncana foran, first appeared here about almost 90 million years ago and went extinct about maybe 72 million years ago, right? So let's say, and this is what scientists first did. They went to the seafloor and they were trying to figure out the age of the ocean floor, right? And so in this example here, we're seeing the Mid-Atlantic Ridge, and we're seeing North America. And remember, seafloor spreading states that new seafloor is formed at the ridge and gets older as you move farther away. And so these numbers, hole 11, hole 10, hole 105, they represent the deep sea drilling project, where they took a ship out to the ocean, had to go through all that water, and then they drilled into the seafloor and pulled out a core of the seafloor. And what they found in those cores, for example, here, this is hole 10, right? That's this hole here. They found they had a lot of chalk ooze, which is foraminifera ooze, or maybe even coccolithophore ooze, and then it sits right on top of the seafloor basalt. So they looked at the fossils that occurred right at the base of the limestone here, right on top of the basalt, and they found these 3 fossils, right? So we want to figure out the age of this unit. And so if we look at the age, we see that those 3 fossils include this Globotruncata Maya, Globotruncata foran. So there's Maya and foran, these 2 here, and then this one here, which is Globigerina, and here's Globigerina. So it's these 3. So it's Globigerina and the 2 Globotruncata's, right? And so our job is to figure out the age range of these, so using a fossil succession. So we see that the first appearance of Globotruncana Maya occurs here, right? And even though these other species go farther back in time, I know the sediment cannot be any older than that, because any older would not have this species in my core sample. And then I see that the limiting factor here is I can't pick anything younger than the time Globotruncana foran went extinct. Even though Globigerina here has a very long span, and Globotruncata Maya has a little bit longer, I can't go any younger than this because this one went extinct at this point here. So what I do here, I can correlate this to go between 84 million years ago and this one comes up here to about 71 million years ago. So the age of this core sample, the core sample for hole 10, the age of the seafloor right here, right on top of the basalt, is older, between 71 and about 84 million years old. So it's going to be in that range, and probably a little bit older because basalt obviously formed before, because remember, the basalt occurs underneath, right? So that's how we use these fossil age ranges to determine the ages of geologic strata. All right, so formative, for example, I just showed you that example, and we've looked at this overlapping age ranges, right? The overlapping age ranges. Now, note that these foraminifera that I used are index fossils, right? And what is an index fossil? Sometimes they're called guide fossils, and I want you to know the three criteria. There's three criteria. The first thing is they're easy to identify. When you see it, you know what you're looking at. And you want it to have a widespread distribution. You want it, especially plankton in the ocean. They're all over the place. So that's a really good one. And then you want them to have a short time duration. So easy to identify, widespread distribution, short geologic time duration. So if we go back to our chart here, just looking at these foraminifera up here, these first four, Orbulina, Glabrontala, Ubergerina, and Glabrogerina, the best index fossil is this one right here, Glabrontala, right? Because it has the shortest range, right? Remember, all these are plankton, so they're all over the ocean, right? And you can see it's pretty easy to identify, right? So those are some of the tools we use to determine index fossils. Right? Topic here are unconformities, and unconformities are used in conjunction with relative time, but here we're going to look at missing rocks, a gap in the rock record. There's a hiatus. Your book uses this word hiatus. Either the rocks were there and they were eroded away, or maybe this area was on top of a mountain or a high plateau and was receiving no sedimentation, so there's been no deposition. So there are three types of unconformities. And the three types, there's an angular unconformity. And so note that the angular conformity will have strata tilted at different angles. So the unconformity is right here, right? That would be the unconformity, this boundary or contact between the strata that's horizontal and the strata that's tilted, right? And then here we have some folded strata, but then we have horizontal strata. So again, this becomes the unconformity right there. So that would be the angular unconformity. The second type of unconformity is called the nonconformity. And so the nonconformity basically states where you have sediments on top of crystalline basement. And so remember, the crystalline basement is either going to be a plutonic igneous rock, like a granite, or a metamorphic rock. Both of these, what they share in common is that they formed within Earth. It's a deep process. It doesn't happen up here on the surface. It's somewhere in the Earth at some depth. But sediments are surface features. They form up here. So the disparity is, how do we get sediments on top of the rock that formed at depth? Well, obviously the rock that formed at depth had to be eroded. All the sediment had to be eroded away to expose this rock to the surface. So that takes time. That's a time gap. And so those are the nonconformities. A really good example of one is a Sierra nonconformity, where we have the Sierra batholith right here, the plutons. We have the Hornfels metamorphic rocks there as well. And then we'll have the nonconformity right here, right? So that nonconformity sits right there. And it's also famous because we have a lot of these gravels. And auriferous, well, that AU is a chemical symbol for gold. So these are the gold-bearing gravels. These are the ones where we do placer mining, right? Gold-bearing gravels. And finally, the third unconformity is the disconformity. And this disconformity deals with a true time gap in that we have parallel strata. We'll have a series of parallel strata. Note that it's different than the angular unconformity because we have different angles here, right? So here we have a sequence of parallel strata, but we note that there's something missing or something doesn't make sense. And as geologic detectives, we're going to be able to figure out what's missing here, right? So if we think about the fossil record, here we have fish, maybe some lungfish, amphibians, and mammals, and modern mammals. So something is missing in this order, this stratigraphy of rocks, right? We're missing the reptiles, right? And the reptiles should belong right in here, right? So the reptiles are missing in our sequence of organisms. And so that must mean that this region here is a time of either erosion or non-deposition. So this would be the disconformity, a time gap that's missing, right? Now, because of unconformities, the rocks presented in the rock layers is incomplete. So no single location on Earth contains a complete record of Earth's history. So in order to figure out the rock formations of planet Earth as a continuous feature, like we show in the geologic column, we need to have correlation, right? And correlation is we're going to match rock units from one area to another, right? So here we'll look at some unconformities. This is actually the Grand Canyon. And here we have the Top Peak Sandstone, which is a sedimentary rock. It's a sandstone. There's trilobite fossils in here. It's Cambrian in age. And here we have the Unkar group. The Unkar group, sometimes called the Grand Canyon group, are a series of Precambrian sedimentary rocks. And you see that they occur at two different angles. So that's an example of an angular unconformity. This next picture here shows a disconformity. Here we see, again, the progression of ammonoids as they start off with straight shells and progressively have their shells curved over time. And then here we're missing a big segment of it. So this would be the disconformity, an erosion event here, right? Then for the Sierra batholith, like I was showing you earlier, note that here are the metamorphic roof pendants, right? The roof pendants. Here is a batholith, right? And here are the plutons. And so remember, these formed at depth, right? Metamorphism and plutonism occurred at depth. And then this line right here is the Great Sierra Nonconformity. And you can see these gravels there would be the ore gravels, the gold-bearing gravels. Then kind of looking here at the nonconformity in the Grand Canyon, right? So here is a Top Peak sandstone. In this part of the Grand Canyon, the Top Peak sandstone sits on top of the crystalline basement, which includes the Vishnu schist, which is a metamorphic rock, and a younger rock called the Zoroaster granite, which intrudes into it. And so these rocks range anywhere from 1.4 billion years old to about 1.7 billion years old, right? And so this boundary here, because remember the Top Peak sandstone is about 540 million years old, so there is a huge time gap. I was fortunate enough to be able to raft the Grand Canyon and actually go to this great nonconformity, right? So here I'm looking at the Vishnu schist, the metamorphic rocks, and here is a Top Peak sandstone, the erosion event and the sedimentation of a new unit here. And so my finger is touching, well, if that's 540 million years old and this is 1.7 billion years old, I'm touching about 1.2 billion years of history that's missing right there. Again, we're looking at the Vishnu schist. Here's that great nonconformity with a Top Peak sandstone on top of that. Now here's a view of the Unkar group, which is that those sedimentary units which are tilted, and you can see the Top Peak sandstone on top of it. So that's the nonconformity, right? Or actually, this is an angular unconformity right there.